Hi, welcome to ESI 521 Pattern Generation at the Nanoscale. I'm Professor Ukjun Nam at the Pennsylvania State University. This is the first unit. In the first unit, I will give you general information about the lithography, and then lecture 1 is for the introduction of the lithography. So here is the outline for today's lecture. I'll give you some kind of a brief introduction of lithography, and then I will give you some examples about the technologies. Lithography, actually that word originated from Greeks, and then that is an litho's plus graphenes. So the meaning of that is stones and then to write. The whole meaning of the lithography is the writing something using a stone or a metal plate. That's the kind of meaning of the lithography. This kind of technologies, as you can see, this is the microelectronic images of the transistor devices, and then as you can see, this is the year. So as time goes on, the size of the transistors getting smaller and smaller, and right now we are in the range of 22 nanometers, which is the smallest feature size used for that kind of microprocessors. Since this technology is kind of driven by those microelectronic industries, so that is why we call the techniques those kind of industries are using. They are using optical lithography as a standard lithography technique for pattern transfer. In another word, we use this original optical lithography as a traditional lithography. In Unit 1, I'm going to talk mainly about the current technologies used for those kind of microelectronics industries. And we do have 5 units for this course. For the Unit 2, I will move the topics to the direct writing lithography. So the example of those kind of technology is an electron beam lithography, and then ion beam lithography, and then deep pen lithography. These all 3 lithography techniques are using direct writing. And then the Unit 3, I'm going to talking about nano imprinting lithography, which has UV and thermal nano imprinting lithography. Unit 4, this is not conventional lithography technique, but this Unit 4, I will introduce you to the block-polymer lithography, and then nanosphere lithography or DNA origami, which needs self-assembly, molecular self-assembly techniques. And then the last unit, I will introduce a little bit about the additive manufacturing. The example of this technique is 3D printing. Actually, the resolution of this technique is not nanoscale, but still there are a lot of kind of researches going on to reduce the size approaches to the nanoscale. And then since this approach is kind of very new and interesting, so I would like to include this technology as the last of this course. So what do we need for the pattern transfer? For a pattern transfer, we need design and pattern. So we need to know what kind of designs we want to make. And then we need some sort of the energy, those kind of reaction is happening to making those kind of pattern. And then we need some kind of materials which will eventually holding that kind of a design we're thinking about here. So let's talk about the design and pattern. So the first form of the pattern is a physical mask. So as you can see in the picture, this one is a UV nano imprinting mold. So it's kind of very hard to see because this entire square is made out of quartz, which is very transparent. And then inside of this quartz plate, there is an active cell areas, and then the actual device is kind of hard to see because the structure itself is in a nanoscale, so it cannot be observed by the naked eye. So this kind of a physical mask, this one is for the UV nano imprinting mold, and then this another mask is a photo mask we use for the optical lithography. And then there is another kind of a form of the mask, which is the shadow mask made on the stainless steel. So I will show you that shadow mask. So so I will zoom out a little bit. So this is the kind of a pattern. So the inside of the white rectangle, that is an open space, and then the rest of the silverish color is made out of the stainless steel. So this kind of shadow mask cannot make those kind of nanoscale features, but this is one of the example of those kind of physical masks for the pattern transfer. So I just want to include this shadow mask as well as a example of the physical mask. So in addition to these two, photo mask, shadow mask, and then imprinting mold, there is another kind of physical mask used for the X-ray lithography. But all these kind of masks used for has those kind of patterns already inside of this kind of physical structure. So we only need to load this mask for your process, and then just to apply some energies to transfer these patterns to the some of the materials. And then I will give you some examples during the later of these lectures, how people are using this kind of a mask to making a pattern transfer. But that's the kind of a basic way people are using. And some of the technologies like direct writing technology, E-beam, laser, ion, or deep pen lithography, even for the 3D printing, it does not need any physical mask. We will go through more details about this kind of electronic version of the design information during next lecture. But technically, this form of the design is stored as an electronic file. So the machine directly connected to the computer just directly draw such lines as we draw into the electronic file. So the electronic design file is another form of the mask we can just use for the lithography. And then the last form of the design or pattern is a material itself. So for the lithography technology, such as block polymer lithography or nanosphere lithography, we already engineered the materials we wanted to define, such as some specific kind of a structure. So the material itself has some specific information to making such a structure. And then this picture shows the patterns made out of the block of polymer. So for making this kind of hole patterns, which is hexagonally arranged, we used this specific polymers, and it has two areas which has material A and material B. So that is why we call this string of the polymer as a diblock polymer. So just changing the length of this polymer, or the ratio of A materials and B materials, we can make this kind of a hole patterns, or we can also make some kind of a lamellae structures. And we will go through more in details about the process and then engineering this kind of materials during the unit later part of the lectures in Unit 4. So when we have designs or patterns ready, we need another kind of component, and that is an energy. So for the optical lithography or UV nano imprinting or X-ray lithography, we use photon energy. So those kind of photons kind of pass through those kind of physical masks, and then some areas is covered by non-transparent materials, and then there is some transparent area. So using those kind of transparent and then non-transparent area, we can transfer the pattern. And electron beam or ion beam also can be used. And then for this kind of source of the energies used for the E-beam lithography or ion beam lithography, or those kind of direct writing technique. And this molecular interaction, that is an intermolecular or intramolecular interactions among the supramolecules. So the example is on van der Waals force and then hydrophobic forces. So using this kind of interactions between those kind of supramolecules, those kind of molecules can self-align without using any external forces or energies. So this kind of energies can be used for the block of polymer lithography or nanosphere lithography or DNA origami. So the last form of the energy is a thermal or mechanical energy. So this kind of energy can be used for the thermal nano imprinting. And then we will talking about this technology in the later unit. And then we need some materials which eventually will hold the design. So this picture, optical microscopy pictures, shows the one of the examples. So what you are seeing right now is the bar pattern, which is this image is made out of the photoresist. So this is the patterns. Actually, inside of the bar is silicon, and then the outside of the bar is covered by the photoresist. And then this is the one of the example of the material which holding that kind of original design, which either has electronic form or physical mask, or this, in this case of that, this is not from the just the material itself. So we do need those kind of three component for the pattern transfer. That is an energy, design, and then material. And then I will give you some example about that three component using the contact lithography, which is one of the technique used for the optical lithography. So, for this kind of optical lithography or contact lithography, what do we need? We need a light source, and then we need a physical mask, and then the material. So physical mask is a photo mask in this case, and then the energy source for the optical source is the photon energy, and then we are using photosensitive polymer coated on a substrate which will work as a material. So for this pattern transfer process, we will need these 8 process steps. So we need substrate cleaning and baking, and then apply adhesion perimeter layer, and then spin coat the photoresist, which is a photosensitive polymer. After spin coating of the photoresist, we need a soft bake, and then UV exposure, and then we will develop that UV exposed photoresist, and then we will do some inspection, and then this is an optional process, but for the depends on the following processes, we might need this optional hard bake process as well. So more details about this kind of processes. The step 1, we will do the substrate cleaning. So before any process, the substrate must be very clean. So it should be fingerprint free, and then specifically the particle is kind of a very cause serious problem, because we will spin coat those kind of resist. So let's say this is a wafer, and then if we have this kind of particles around, if then when we apply the resist in the center, and then as we spin the substrate, those kind of resist will spread out, and then eventually will cover entire substrate wafer. But if there is some kind of particles present, when this kind of liquid phase photoresist spread out to the wafer substrate, it's just making some kind of boat mark. So inside, actually this particle just blocked the spread of this kind of uniform spread of this kind of photosensitive layers, and then the inside of this kind of conical shape, the thickness of the resist is kind of much thinner. So this area, and then the area the particle is sitting on, the patterns on that area might be damaged, so will not be properly transferred. Actually, we discussed about more kind of cleaning method in the previous ESI 1-2 lectures. So, but when we use the substrate coming from a kind of a fresh new wafer box, we only use these 3 steps: acetone, IPA, and DI water rinse. So the acetone rinse just to remove the organic or particles, and then the IPA removes the residue of the acetone, and then the DI water dissolves the IPA, so remove the residue of the IPA. So after this kind of a cleaning process was done, we first dry the substrate using nitrogen gun. But this nitrogen gun cannot completely dry out the substrate. So after this nitrogen gun blow, we still have some moistures left on the substrate. So we put the substrate on hot plate and then do an additional dehydration bake. So after the dehydration bake, we cooling down the substrate, and then we apply adhesion promoter, which increase the adhesion between the photoresist and substrate. The most common form of the adhesion promoter is the HMDS, which is an hexamethyl disiligane. And this is the primer. So we apply these materials while spinning the substrate, and then after we coating these materials, we bake this layer on hot plate around longer than 15 seconds at 105 seconds. And then after this baking, we cooling down the substrate again. So after this process, we will have a very thin layer of the HMDS layer on top of the substrate. So this is how HMDS is working. So this is the HMDS. So when these molecules see the OH bond on silicon wafer, this NH just stealing hydrogen and then just making ammonia. So this bond is removed, and then here is one free bond over here and another free bond over here, and then this bond just directly connected to oxygen. So using that way, you can just making. This one is an HMDS layer, and then this is the silicon wafer in this example. So this is the way these kind of molecules forming those kind of layers on top of the silicon wafer, and then these molecules can make very strong bond with photoresist, which will be coated later on top of this layer. So for this example, I'm going to use a positive tone photoresist. So the details will be explained in the later of the lectures, but positive photoresist initially has a very good cross-link among the polymers. Upon these polymers exposed by the UV light, those kind of high energetic beams cut those kind of cross-linked. So so those kind of areas exposed by the UV light, since those kind of polymers were cut, is kind of a cross-link. During the following development process, this specific area exposed by the UV light will be removed. So for this one, we use the same kind of a process we used for the HMDS coating. So in spin coating, spin coater, it has this kind of a vacuum chuck. So on vacuum chuck, on the top, it has a circular shape, and it has this kind of channels, so which can just apply the vacuum. So using the vacuum, we can just hold this kind of substrate tightly, And then we can apply the resist from the top. This can be a void, or there is some kind of a dedicated tools for industries. They are using some kind of automated kind of tools for applying this kind of photoresist. So there are two ways of applying this coating this kind of materials, and then that is static, and another one is a dynamic coating. So the static coating is applying those kind of a photoresist when the substrate is stopped. And then once we apply the photoresist, first we spinning the chalk in a very slow speed. So as those kind of a substrate are spinning, those kind of liquid phase photoresist started to move, but it started to accumulate at the edges. At a little bit higher spin speed, it just moves a little bit faster, and then just making this kind of structures. But eventually, even at that high speed, at the edges, those kind of photoresist are making this kind of a bead structure, which is a little bit thicker than the other areas. So both static or dynamic coating, this is the kind of strategies what people are using. So this is a time, and this is a spin speed. So in the static, we apply the photoresist at when the chalk is stopped. So the spin speed is 0. And then we just spin the chalk in a very slow speed, which is about 900 RPM. So in these stages, those kind of photoresist just move. And then we quickly increase the speed, and then which is on about 2000 RPM, about 2 or 3 seconds. And then we increase the spin speed to the final speed, which is on about 4000 RPM or higher. The reason why we have this kind of intermediate spin speed is with this kind of very short time is using this speed, this kind of a bead just removed. We call that as a spit out process. So in that spin speed, we kind of a low spin speed, about 900 RPM. We just have this kind of a good accumulation of the photoresist. And then this kind of a speed out process, those kind of bead structures just removed. And then finally, in this kind of very high spin speed, it has a much smoother film formation because we already removed the bead at the intermediate spin speed. This strategy applies the same to the dynamic coating. So only differences between static coating and dynamic coating is we apply the photoresist in this stage when the substrate was slowly spinning around 500 to 900 RPM. But even this kind of dynamic coating need this intermediate spin speed and then final spin coating speed. So as we just keep spinning, if we are seeing the film from the top, we will see the color of the film is kind of keep changing, and then this is the substrate, and then we will see the colors seems like spread out from center to edges, and then for a while, less than 30 seconds, it depends on the viscosity of your photoresist and then the thickness, but usually it happening during first 30 seconds, and then the color of the film is keep changing. That's because of as we keep spinning the substrate, the solvent inside of the photoresist is keep evaporating. So that is why as the solvent inside of the photoresist is keep evaporated, the thickness of the photoresist is getting thinner. And at some point, you will not be able to see any color changes. That's because the solvent will evaporated, and then it just reaches to the stabilized state. But still, after this spin coating, the photoresist has quite amount of the solvent inside of the film. So that is why we need following soft bake. So the baking condition is different based on different kind of photoresist, but normally the usual condition is on 90 seconds around 105 Celsius degree. So the purpose of this soft bake is prevent from the exposure interference, and then the baking make the adhesion, improve the adhesion between the photoresist layers and then substrate. And then since this substrate photoresist is still very soft, in the contact lithography, in the case of that, those photo mask directly contact the photoresist. In the case of that, some part of the photoresist can be peeled off by the contact of the by the mask. So to prevent for that kind of reactions, we use the soft bake, and then that is pretty effective for doing that. So depends on you already have a patterns on your substrate or not. We need to do an alignment of the pattern to the pattern already on the substrate. And then once we complete the alignment, we will do a UV exposure. So we do have a substrate. We might have some kind of a film, processes from the earlier steps, and then this is the photoresist we just coated and then do the soft bake. And then we put the masks directly touching the photoresist, and then this pink color is over the UV light. And then some of the area was the UV light was blocked by the chromium, and some of the area where there's no chromiums present. So in these areas, the UV light can directly go to the photoresist, and then which energetic UV light will cut the cross link of the photoresist. So after this exposure process, as I mentioned before, those UV exposed area, those cross link of the polymer was already cut. So during the following wet chemical processes, those areas, the polymers are removed. So those areas exposed to the UV light, the polymer was removed. So after this, we will rinse the substrate in the eye water, and then dry it using the nitrogen gun, and then we do the inspection. So in this inspection, we will check if those patterns aligned very well. that's the one thing. Alignment is the one thing we are inspecting, and then we will also see if there is some areas kind of damaged by the during the process. So we normally use an optical microscope to do this inspection process, and then if that apparent transfer is not acceptable, we need to remove entire resist layer up, and then reapply the photoresist, and then repeat the this parent transfer steps again. So this is the inspection. So we also check if this is an underdeveloped and then overdeveloped. That means this is the closely related with the exposure time, the UV exposure time. So in the initial stage of the getting the conditioning of the lithography, we varies the from shorter time to long time. So we have some kind of time intervals, and then we check which exposure time is the right, giving the right kind of a parent transfer. So that's the one of the step we need to go through for the initial stage of the photolithography process. So depends on the following steps, we need to do the hard bake. So again, the condition for the hard bake vary based on the different kind of photoresist, and then the purpose for that hard bake that highly depends on the next process step. But the typical condition is about 1 to 5 minutes bake at 120 Celsius degree on hot plate. So the hard bake offer further improvement in adhesion, and then it just to make the photoresist layer harder. So it just to give a much higher resistance over the following, if the following process is a dry etching or something like that. So in the first lecture, I just talked about what is the three components needed for the parent transfer, and the design, and then energy, and then material, which eventually holding the transferred pattern. So next lecture, I will talk about a little bit more about the design patterning. So I will just go through more details about how we create those kind of electronic design, and then how we are making those kind of photo mask. And then to this kind of energy part, we will discuss about, since we are using very different type of the energies, depends on the lithography techniques we are using. So we will discuss about this energy part as we go over each of the different kind of a unit. So thank you for your attention, and see you next lecture.